Hi everyone, our team is Dusk to Dawn, and my name is Zach Hatzenbeller.
I'm Kendall Rusnak.
I'm Braeden Boyer.
And I'm Lindsay Patla, and this semester our project was the production of dimethyl ether from an impure methanol feedstock.
In today's presentation, we will discuss the location, capacity, and specifications of our process plant. We will then transition into discussing the process that we've developed, as well as the economics for our process, and then give you recommendations based on what we've learned from our process. So the main reason that we're deciding on producing and selling DME is basically as a substitute for diesel fuel in transportation. So diesel fuel, as we know, is a non-renewable fossil fuel, while DME can be made from renewable resources such as biogas or even natural gas and carbon dioxide. Another reason that we're looking to produce DME is because of the carbon emissions. So the carbon emissions compared to diesel fuel are much lower, making it much more environmentally friendly. So our plant is currently being designed to produce DME at an already existing site. It's located on the Gulf Coast, and the capacity that we're aiming to produce at is 15,200 pounds per hour. The incoming feed is around 90% methanol, and that's being transported to the site via rail.
To begin the process overview, the raw materials stream first enters an ion exchanger to remove the corrosive chloride ions that could potentially be harmful to the different materials of construction, specifically stainless steel. We had to decide on a resin to use, and we went with the Dowex Marathon A because it has a relatively high temperature that it can withstand, and also because it exchanges the chloride ions with hydroxide ions. The hydroxide ions will react just to create more water, which is already present in the process, so it won't create any different types of reactions that we're not expecting, and it will be easy to deal with. Then this enters the first two feed separators, our first two distillation columns. We decided to go with two identical distillation columns because there's a high flow entering, and also to minimize the reflux ratio. This will then go into a reactor. There's two reactors in parallel. Their size is 4 feet high and a 4 foot diameter. They're identical as well. And we went with two in parallel so that the process would be continuous and it didn't need to be stopped and shut down and then restarted. When the alumina oxide catalyst is used up in one reactor, then the feed will then just go to the second reactor without having to be stopped and restarted. The reactor effluent will then go into a third distillation column, the DME separator. The DME separator is very easy to separate because DME is very volatile and has a low boiling point of about minus 12 degrees Fahrenheit, so it can be separated easily, and the bottoms, which is water, ethanol, and acetone, will go to a fourth distillation column. The fourth distillation column will try and remove the acetone on the tops and the ethanol and water on the bottom to be recycled. However, the acetone and ethanol will create an azeotrope, which is hard to overcome. Throughout our research, we could see that water being added would help overcome this azeotrope, which is already present. So then the bottoms will be recycled into the feed to go into the first two feed separators. We came across two main problems throughout our project. The first being that it's hard to store DME because it has such a low boiling point that to store it in the liquid phase, it needs to be at an extremely high pressure and low temperature, which is very costly to our system. Secondly, and probably the largest problem that we came across, is that we aren't doing anything with our waste streams. They are just being wasted. We decided not to purify them because with such low flow rates, it would drastically increase our capital cost, and it wouldn't be beneficial to our team to purify them and sell them or recycle it back into the system.
As mentioned, the impure methanol feed is sent to two identical distillation columns before being sent to reaction. These distillation columns separate methanol and acetone off the top of the column and water and ethanol to the bottom. The water and ethanol create a low-pressure azeotrope and are very difficult to separate. For this reason, this separation was decided early on for us to not try. Removing the water before reaction ensures that the reaction will proceed further to completion. Water inhibits the reaction, and the ethanol, removing the ethanol ensures that no ethanol-based side products will be created. Initially, one column was used, but due to the large vapor flow and large reflux ratio that was required, the column was split in two as the diameter was too large to ship in. Shipping in distillation column pieces is very important, as building a distillation column on site can be very expensive. The reaction used to turn the methanol into dimethyl ether is a dehydration reaction. Two methanols create one molecule of dimethyl ether and one molecule of water. Other notable side reactions in this process are the decomposition of ethanol into dimethyl ether as well. After the feed is split in the two distillation columns prior, this mixture is then sent to reaction. This mixture contains 89.3% methanol and the remainder acetone. The feed enters a system of two parallel reactors. One reactor is run at a time, as the other is saved for times of maintenance and to regenerate catalyst. The dehydration reaction is done in the vapor phase, and the effluent of the reactor is used to preheat the feed, as well as high pressure steam, to ensure that the feed is in the gas phase before it enters the reactor. To overcome the activation energy, a catalyst is needed. A gamma alumina oxide catalyst is used and packed into a basic fixed bed adiabatic plug flow reactor. The reactor converts approximately 83% of the methanol into DME, while the acetone generally acts as an inert. The next section of our system is the DME separation. This column fractionates DME through the distillate with a purity of 98.6% by mass. Due to DME's high volatility, this separation is very simple and very economical. The DME is pulled off as a vapor and then compressed and cooled until a liquid phase is reached. Storage should always be in a liquid phase for things such as this. Currently, the DME product meets all hard specs for water, methanol, and sulfur contents. The residual components of the separation are then sent through the bottoms of the column to another separator. Our final separation removes acetone from the system. This removal of acetone ensures that there will be no inert buildup within the system. Acetone and methanol generally create an azeotrope when mixed. One way to overcome this azeotrope is to do an extractive distillation. By adding a third component to the system, the azeotrope can be overcome by separating one from a set of another two. In this case, water is used as our third component, our extractant. Due to the dehydration reaction in the system, water is created, and this allows us to not have to pay for water or add water to the system. It creates a natural extractive distillation. The bottoms of the column, containing mainly methanol and water, are recycled and mixed with the impure methanol feed and sent to the first set of columns.
As a result of this base case design, our plant is able to produce an on-spec DME transportation fuel, which meets hard specs for both methanol, ethanol, water, and other contaminant concentrations for sale on a U.S. transportation fuel market. We are also able to add lubricant additives to this fuel to meet specifications for the U.S. Department of Transportation as well. Where the design falters is in the handling of side product waste streams, which are not purified to meet market specifications. These are thus burned as fuel or other waste and are not sold profitably outside. So this is an area that the design lacks.
So our current plant design is not profitable mainly due to the waste streams. The reason for this is that the waste streams are not integrated into the process and are just being disposed of. This is losing us a considerable amount of money due to the raw materials expenses. As you can see on the pie chart, the raw materials expenses make up around 79% of our yearly expenses. Looking at the IBL capital costs, these are also very substantial. The compressors make up a large portion but contribute the smallest amount of units to the plant. This capital cost would only increase if we decided to further purify the waste streams, which is why our team was hesitant to pursue this option at first. Kendall will talk more about this purification in our alternative case that we also considered.
OBL, or the outer battery limit capital costs, are also needed to be factored into the plant's total capital. The main contributors to this cost are the product storage facilities needed and the increase in cooling water needed. While evaluating the economics, we found these costs to be slightly higher to the IBL capital costs by around $2 million. This really inhibits any profits that may have accumulated within the first few years of production and puts the plant's economics more in the red. OBL operating costs also need to be accounted for. While the expenses are not substantial for these operating costs, they are on a yearly basis and add to the large losses we see over the course of the plant's lifetime. In the end, decreasing the OBL capital would make a significant difference in the first few years of the plant's life and allow for more revenue to be generated.
Looking more broadly at the plant's economics, we can see that there are continued losses over the 15 years of operation. The cumulative cash flow chart shows a small decline within the first few years of production, proceeding to a sharp decline around 2010 to the end of the plant's life. The main contributors to the large losses we see in this plant are the raw materials and utilities costs, which are on a yearly basis. The capital required is planned to be paid off within the first 5 years of operating, which would be beneficial except for the fact that the plant is losing money each year. To examine this further, the main reason for the raw materials costing so much is due to the incoming feed flow rate being double the amount of product that is actually sellable. The price for the incoming feed is around 13 cents per pound, while the price to sell the product is only 21 cents per pound. Since this is not double the price, we expect to lose money each year.
In addition to the base case model outlined earlier, our group also explored an alternative case design in which 2 additional distillation columns were added to the original case discussion. The first waste separation took the bottoms of the first feed column and allowed for a majority of the methanol to be recovered and fed into the reactor, with a more pure water waste being expelled out the bottom. This allowed for a reduction in the amount of fresh feed that was required in this design, and that was also assisted by a second, we'll call it a waste separation 2, in which the bottoms of the acetone separation column drew a water and organics waste stream, as well as another recycle to be added into the front end, and that water and organics to be separated by that original column. These overall yielded a more profitable plant design by approximately $50 million over a 15-year runtime. However, this design was not as promising as initially thought because the increased capital costs from 2 new columns, as well as the large amount of utility duty required for those condensers and reboilers, offset the reduction in size and reflux ratio that the original units were able to do in this design. So looking at yearly expenses, this alternative design has a raw material value that decreases by about 3%, or almost 3% of the overall value, but 30% in total cost. But utilities now make up a much larger portion of the costs in this design. So overall, it's worth exploring as it saves money, but is not overall, it's not a complete winner. After all process and economic evaluation of this plant design, it was determined that our plant would operate at a yearly loss of over $11 million per year. This points to the fact that under the current economic and global conditions regarding DME and the methanol feedstock used to fuel this process, this plant should not move forward within the construction phase. During a sensitivity analysis, it was found that a 50% increase in the DME product pricing, with all other factors holding the same, would allow us to simply break even after a 15-year runtime. With this in mind, our group recommends that unless major economic and other factors change within the world, this plant should not proceed out of the design phase at this time.